Hi there, welcome to Ancient Cosmos Sleep. Tonight we leave the familiar comfort of Earth behind and drift into a quiet corner of the universe where two enormous islands of stars slowly approach one another through an ocean of darkness. You float gently above our little blue world, watching continents disappear beneath clouds until even the sun becomes just another bright star among countless others. Ahead, a faint smudge grows, ever so slightly brighter, almost shy, yet hiding a size so extraordinary that your everyday intuition simply gives up trying to measure it. It's the Andromeda Galaxy, our closest giant galactic neighbor, and tonight you'll discover just how astonishingly large it truly is. You probably won't survive the trip there, mostly because 2.5 million years is an inconveniently long commute. Space has terrible public transportation, so before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And while you're settling in, let me know where you're listening from and what your local time is. It's always wonderful imagining listeners scattered across our own tiny planet while we explore something unimaginably larger together. Now, dim the lights. Maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You begin by shrinking your sense of importance, though not in a gloomy way. More like realizing you've brought a teaspoon to measure an entire ocean. Earth becomes a tiny marble. The Solar System becomes a delicate ring surrounding a perfectly ordinary yellow star. Even the enormous cloud of icy comets surrounding the Sun fades into the darkness behind you. Ahead stretches the Milky Way. From inside it, your home galaxy feels endless. Ancient civilizations looked up and saw its pale ribbon crossing the night sky. The Greek philosopher Democritus imagined countless worlds beyond our own, while centuries later, Galileo Galilei pointed a telescope toward that glowing band and discovered it was made of innumerable stars rather than some mysterious heavenly mist. That simple observation quietly transformed humanity's understanding of the cosmos. Yet even the Milky Way, magnificent as it is, isn't the largest thing nearby. That honor belongs to Andromeda. At first glance, Andromeda seems almost disappointingly modest. Under dark skies, away from city lights, you might barely notice a fuzzy oval hanging in the constellation that shares its name. You could easily mistake it for a tiny cloud that forgot to keep moving. Meanwhile, that little cloud contains roughly 1 trillion stars. Yes, 1 trillion. Your brain politely thanks you for the information before refusing to picture it. And honestly, that's understandable. Humans evolved to estimate things like how many berries fit into a basket, or whether that mammoth looked grumpy enough to avoid. Nobody evolved to comfortably imagine 1 trillion suns gathered into a graceful spiral stretching across hundreds of thousands of light years. So tonight, instead of drowning in giant numbers, you'll build intuition piece by piece. Imagine standing on a quiet beach at night. The horizon feels distant, but you can still understand it. Now imagine replacing every grain of sand with another beach. Then replace every beach with another coastline. Eventually, comparisons stop helping, and that's where astronomy begins. Astronomers often describe galaxies as island universes, a phrase popularized in the early 20th century after people realized the spiral nebulae seen through telescopes were actually separate galaxies far beyond the Milky Way. Before that breakthrough, many believed our galaxy comprised the entire universe. Historians still argue whether some earlier thinkers came surprisingly close to this idea but the evidence remains incomplete. That realization was humbling, not because humanity became less special, because reality became wonderfully larger. The Milky Way itself spans roughly 100,000 light-years across its bright disk, perhaps more, depending on exactly where astronomers decide its visible edge ends. Already, that's an absurd distance. If light, the fastest thing in the universe, needs 100,000 years to cross it, imagine attempting the journey in a family hatchback. You'd probably run out of snacks before leaving the driveway. Actually, you'd run out of civilization first. Even if every generation continued driving forever, nobody would arrive. And yet Andromeda appears to be even larger. Not dramatically larger in the way an elephant outweighs a mouse, but enough that astronomers have spent decades refining exactly how far its outer regions extend. As observations improve, Andromeda keeps revealing faint structures farther and farther from its glowing center, almost like unfolding a blanket you thought was already fully opened. One charmingly strange fact is that some astronomers affectionately refer to these extremely faint outskirts as stellar ghosts. Because they are so sparse and dim, they barely reveal themselves even through powerful telescopes. Space, it turns out, enjoys understatement. You continue floating farther above the Milky Way until its graceful spiral arms slowly become visible beneath you. Clouds of glowing gas curl through the disks like pale ribbons. Dark dust lanes twist between billions upon billions of stars. Then you notice something ahead. Another spiral, larger than you expected. Much larger. This is Andromeda, known scientifically as Messier 31, or simply M31. It isn't randomly scattered somewhere in space. It belongs to the same family of galaxies as the Milky Way, called the Local Group. Think of it as the largest neighboring city in a very quiet countryside. Except the cities are galaxies, and the roads between them are millions of light-years long. Despite all that emptiness, gravity patiently continues its work. It never hurries. It never complains. It simply waits. Every second, Andromeda moves a tiny bit closer to us. Not enough for you to notice tonight. Not enough for your great-great-grandchildren. But enough that over billions of years, two giant spiral galaxies will eventually meet. We'll save that extraordinary encounter for later. For now, simply admire Andromeda itself. Its spiral arms curve elegantly around a bright central bulge. Blue clusters mark regions where young stars shine brilliantly. Older golden stars crowd toward the center. Vast clouds of dust weave graceful patterns through the disk, quietly preparing future generations of suns and planets. If you somehow hovered above it safely, the galaxy wouldn't feel crowded at all. Quite the opposite. Stars are astonishingly far apart. Even inside this enormous city of light, most of space remains almost perfectly empty. It's one of astronomy's favorite surprises. Galaxies look packed together in photographs because cameras compress incomprehensible distances into flat images. In reality, the nearest star to our Sun lies over 4 light-years away. Inside Andromeda, the story is much the same. Immense populations of stars, yet oceans of darkness separating nearly all of them. A little like owning the world's largest neighborhood, where every neighbor lives on their own continent. Not exactly ideal for borrowing sugar. As you quietly observe this giant spiral suspended in darkness, you begin realizing that asking, "How big is Andromeda?" isn't really asking for a single number. It's asking how humans measure the nearly immeasurable. It's asking how something appearing smaller than your thumbnail can secretly outweigh and outstretch anything you've ever known. Most importantly, it's asking you to gently stretch your imagination until it becomes just a little larger than it was an hour ago. And this is only the beginning of the journey. The faint smudge you've occasionally seen in photographs is no longer merely another galaxy. It's becoming a place with structure, history, motion, mystery, and a scale so vast that every answer naturally leads to an even bigger question waiting just beyond the next quiet stretch of cosmic night. The Milky Way slowly fades into the background behind you, not because it has become smaller, but because your attention is gently drawn toward the soft glow ahead. From this distance, Andromeda looks surprisingly delicate. It doesn't announce itself with blazing colors or dramatic explosions. Instead, it resembles a faint brushstroke painted across an impossibly dark canvas, almost as though the universe whispered instead of shouted. That is one of the greatest tricks your eyes have ever played on you. You naturally assume that things appearing small must actually be small. A bird crossing the sky looks tiny because it is tiny. A distant airplane becomes a speck because it is far away, but you already understand airplanes. Your brain quietly corrects for the distance. Galaxies refuse to cooperate with this habit. Andromeda appears only about 6 times wider than the full moon in Earth's sky. That surprises many people. Wait a minute, you think. If it's that large, why can't everyone see a gigantic spiral stretching across half the heavens? Because almost all of it is too faint. Imagine someone handing you a flashlight whose batteries are almost completely drained. The bulb still glows, but only barely. Now place that flashlight on a distant mountain. You might notice a tiny point of light, but you certainly wouldn't appreciate its full size. The same thing happens with Andromeda. Your eyes are remarkable instruments, yet they evolved for survival on the African savanna rather than detecting diffuse starlight, crossing millions of years of empty space. Under perfect dark skies, you can usually see only the bright central bulge with the naked eye. The enormous spiral arms fade into invisibility because their light is spread so thinly across the sky. Ironically, if your eyes were sensitive enough to detect the entire galaxy at full brightness, Andromeda would dominate the night. Its full apparent width spans several degrees across the sky, many times wider than the moon. The universe has been hiding something gigantic in plain sight all along. Ancient skywatchers noticed this mysterious fuzzy object long before telescopes existed. The Persian astronomer Abd al-Rahman al-Sufi described it around the 10th century as a little cloud in his famous catalogue of stars. That simple description remained remarkably accurate for centuries because no one possessed instruments powerful enough to reveal its true nature. Imagine looking at one of the largest structures visible to the naked eye in the universe and politely calling it, "that little cloudy thing over there." History has a delightful sense of understatement. Of course, later astronomers pointed increasingly powerful telescopes toward it. At first they saw more detail, but still debated what exactly they were observing. Was it a nearby cloud inside our own galaxy? Was it some kind of strange stellar nursery? Historians still argue whether certain 19th century observations hinted strongly enough that Andromeda lay beyond the Milky Way, before definitive proof arrived decades later. Science often advances through gradual confidence rather than one dramatic revelation. One particularly quirky story involves early observers sketching Andromeda by hand over many nights. Tiny imperfections in their drawings occasionally turned into imagined structures that later astronomers couldn't find at all. The universe wasn't changing, the pencils were. It's comforting, somehow, to remember that even brilliant scientists sometimes blamed galaxies for what was really an artistic wobble. As you continue drifting closer, the faint oval slowly gains definition, not rapidly. Nothing in astronomy happens rapidly unless something has gone spectacularly wrong. Instead, delicate lanes of dark dust begin threading through pale spiral arms. Young blue stars gather in luminous clusters. Older yellow stars glow more softly, giving the galaxy a gentle golden heart. From Earth, cameras reveal these breathtaking details because they collect light for minutes or even hours. Your own eyes gather light for only a tiny fraction of a second before sending the information to your brain. In other words, astrophotographers possess an almost unfair advantage. They're basically letting the universe pose for an extremely long exposure. Meanwhile, your eyes glance politely and say, "Yes, that's probably a cloud." As technology improved during the 20th century, astronomers realized something astonishing. Every individual point inside those graceful spiral arms represented countless stars too distant to distinguish separately. Only the brightest giants stand out individually in powerful telescopes. The overwhelming majority simply blend together into soft, luminous ribbons. Think of looking at a distant city at night from an airplane. You don't see individual light bulbs, you see glowing neighborhoods. Now replace every neighborhood with billions of stars. The comparison still falls short. Your journey continues until you imagine standing somewhere far outside both galaxies. Behind you, the Milky Way stretches gracefully across the darkness. Ahead lies Andromeda. For the first time, you can compare them side by side. The resemblance is unmistakable. Both are majestic spiral galaxies. Both possess winding arms rich with gas and dust. Both contain ancient star clusters orbiting their outskirts. Both shelter enormous black holes at their centers. They're cosmic cousins, perhaps even siblings in a very extended galactic family reunion where everyone arrives several billion years late. Family dinners would require extraordinary patience. One interesting curiosity is that Andromeda is actually moving toward us rather than away from us. Most galaxies in the expanding universe recede because space itself stretches between them. Andromeda is different. Its mutual gravitational attraction with the Milky Way is strong enough to overcome that local expansion. It's as though two leaves floating on a slowly widening river somehow drift toward one another instead of apart. That peculiar motion fascinated astronomers once they measured it using spectroscopy, a technique that analyzes the colors of light. Light itself carries information. When a galaxy moves toward you, its light shifts slightly toward the blue end of the spectrum. When it moves away, the light shifts toward red. The effect is tiny but measurable, like hearing the pitch of a passing ambulance change as it drives by. Except instead of sound waves, you're studying light that has traveled for millions of years. The universe whispers its secrets. Scientists simply learn how to listen. Meanwhile, you continue appreciating something wonderfully simple. Distant changes perspective. A mountain viewed from an airplane becomes a wrinkle. A continent viewed from the moon becomes a patchwork. A galaxy viewed from Earth becomes a faint smudge. The object never changes. Only your viewpoint does. That's one of the quiet lessons hidden inside astronomy. Sometimes reality is unimaginably grand even when it appears almost invisible. As your gaze lingers on Andromeda, you realize the galaxy isn't trying to impress anyone. It doesn't need dramatic fireworks. Its beauty comes from patience. Every star continues orbiting, every cloud of gas slowly evolves, every gravitational interaction unfolds over millions of years with extraordinary calm. You almost envy that pace. No deadlines, no alarm clocks, certainly no emails marked urgent. The stars seem blissfully unaware of quarterly performance reviews. Perhaps they've discovered the ultimate work-life balance. You smile at the thought before returning your attention to the glowing spiral. Now that you've learned why Andromeda appears so modest in Earth's sky despite its immense true size, you're ready for an even more astonishing realization. The light reaching your eyes tonight has been traveling longer than human civilization has existed. Much longer. Every photon is an ancient traveler, carrying a story that began long before modern humans built cities, wrote books, or imagined galaxies at all. And as you quietly follow those patient beams backward through time, the next piece of the puzzle begins to unfold. The ancient light continues its silent journey toward you, crossing the darkness with unwavering determination. You don't notice individual photons arriving. They are far too small, far too quiet for that. Yet every moment, tiny messengers that departed Andromeda around 2.5 million years ago finally complete their extraordinary voyage by landing on your eyes. That number deserves a moment of appreciation. 2.5 million years. Not 2.5 million miles. Not 2.5 million kilometers. 2.5 million years of non-stop travel at the fastest speed the universe allows. Nothing with mass can outrun light. According to the theory of relativity, light in a vacuum travels at nearly 300,000 kilometers every second. Every second. Before you finish blinking, a beam of light could circle Earth more than 7 times. It is astonishingly fast. And yet, compared with the size of the universe, even light sometimes feels almost painfully slow. Imagine switching on a flashlight here on Earth. If you pointed it toward the moon, its light would arrive in just over 1 second. Shine it toward the sun, and the light would take about 8 minutes to get there. Already, those distances stretch the imagination. But Andromeda exists on an entirely different scale. If you could somehow turn on a magical beacon bright enough to be seen from Andromeda tonight, no one there would witness your signal until roughly 2.5 million years from now. By then, every human alive today would be long gone. Every city you know would have changed beyond recognition. Mountains would slowly erode. Rivers would carve new paths. Entire species would appear and disappear. Space quietly laughs at your calendar. It has no interest in weekends. Your vacation request has been respectfully ignored. As you drift farther from the Milky Way, imagine rewinding history while moving through space. Every kilometer backward is also a tiny step into the past, because the farther you look, the older the light becomes. When you look at the moon, you see it as it was about 1 second ago. When you look at the sun, you see it 8 minutes in the past. The nearest star beyond the sun appears as it looked more than 4 years ago. Andromeda? You are seeing it as it existed before modern humans even walked the Earth. That realization feels almost magical. Right now, somewhere inside Andromeda, stars are exploding, planets are forming, and countless events are unfolding. But you cannot see any of them yet. Their light has only just begun its immense journey toward you. It's like receiving a postcard mailed millions of years before your species invented the postal service. One of the most fascinating restical discoveries came when astronomers finally accepted that the universe allows you to look backward through time. Early observers naturally assumed telescopes simply revealed distant places. They do, but they also reveal distant moments. The farther away an object lies, the further back in history you are looking. This idea transformed astronomy from simply mapping the heavens into something much richer. Astronomy became a form of archaeology, not digging into ancient soil, digging into ancient light. Some astronomers affectionately call photons time capsules, although they contain no tiny handwritten messages saying, "Greetings from 2 million years ago." That would certainly make conferences more entertaining. Instead, each photon carries subtle information about the object that emitted it, its temperature, movement, composition, and more. The universe has been sending reports for billions of years. Fortunately, they don't arrive as PDF attachments. You continue floating between galaxies, allowing yourself to imagine the timeline more personally. Around the time the light now entering your eyes first departed Andromeda, Earth's climate looked very different. Early human ancestors were still evolving, adapting to changing environments across Africa. Stone tools existed in simple forms, but agriculture, writing, cities and civilizations remained unimaginably far in the future. The dinosaurs had already vanished tens of millions of years earlier, leaving mammals to diversify across the planet. Vast grasslands spread across continents. Saber-toothed cats and giant mammals would later roam landscapes your distant ancestors had yet to fully explore. Meanwhile, Andromeda quietly continued spinning. Its stars orbited the galactic center. Its spiral arms slowly shifted. Its immense gravitational dance never paused. The galaxy paid no attention to Earth's unfolding story, because the universe rarely grants special treatment to any single planet. That thought can feel humbling, yet strangely comforting. Your worries, deadlines, and overflowing inbox occupy such a tiny slice of cosmic history that they almost dissolve against the backdrop of millions of years. The email marked urgent. The bill due next Tuesday. That embarrassing thing you said 3 years ago. Andromeda has been patiently waiting while all of those events came and went. Perspective is one of astronomy's greatest gifts. Scientists determine Andromeda's distance using several clever techniques. One of the most important involves special stars called Cepheid variables. These remarkable stars brighten and dim in predictable cycles. By measuring how quickly they pulse, astronomers can calculate their true brightness, compare that actual brightness with how bright they appear from Earth, and the distance reveals itself surprisingly accurately. It sounds almost like measuring the distance to a candle by knowing exactly how bright the flame should be. Elegant, sensible, brilliant. Of course, astronomers don't rely on only one method. They compare multiple independent techniques, each strengthening confidence in the final result. Science rarely depends upon a single lucky guess. Historians still argue whether some early distance estimates deserved more credit than they usually receive, since several pioneering astronomers came remarkably close despite limited equipment. Even imperfect measurements helped pave the way toward modern understanding. One delightfully quirky fact is that Andromeda's distance has been revised several times over the last century as instruments improved. The galaxy itself never moved dramatically farther away. Humans simply became better at measuring. It's a comforting reminder that knowledge often improves not because nature changes, but because curiosity becomes more precise. As you continue your peaceful voyage, imagine racing alongside one of those ancient photons, second after second, year after year, century after century. It crosses empty intergalactic space where darkness reigns almost completely uninterrupted. Occasionally, it passes lonely hydrogen atoms drifting between galaxies. Mostly, it travels through astonishing emptiness. No traffic, no road signs, not even a rest stop. Perhaps the universe should consider installing a cosmic coffee shop every 100,000 light years. Business might be slow, very slow. Eventually, after millions of uninterrupted years, the photon reaches the outskirts of the Milky Way. It slips between sparse stars, threads past drifting clouds of gas, enters our solar system, glides through Earth's atmosphere, and finally lands inside your eye. Its journey is complete. Yours, however, is only beginning. Because once you understand that looking at Andromeda means looking millions of years into the past, another fascinating question naturally appears. If the light itself takes so incredibly long to arrive, how do astronomers accurately measure something so unimaginably vast in the first place? That elegant answer waits patiently just ahead. The question settles gently into your thoughts as Andromeda hangs before you, enormous yet impossibly far away. You now understand that its light has traveled for about 2.5 million years before reaching Earth. But another mystery quietly takes its place. How can anyone possibly measure something this large? You cannot stretch a measuring tape across a galaxy, even if you owned the longest tape measure ever manufactured. The instruction manual would probably end with, "Please do not attempt intergalactic use." Astronomy has always required a different kind of thinking. Instead of walking up to an object and measuring it directly, astronomers become masters of geometry, patience, and clever comparisons. They build enormous cosmic rulers from simple ideas, stacking one measurement upon another until the impossible becomes surprisingly approachable. Imagine standing at one end of a wide river. You want to know how wide it is, but you cannot cross. Instead, you walk along your own side of the river, measure a few angles, apply a little geometry, and suddenly you know the distance without ever getting your feet wet. The universe works much the same way. One of the oldest and most elegant techniques is called parallax. Hold your thumb at arm's length and close one eye. Then switch eyes. Your thumb appears to jump against the background. Your thumb has not moved. You have. That tiny shift reveals depth. Astronomers use exactly the same principle on a vastly larger scale. As Earth travels around the Sun, our viewpoint changes by nearly 300 million kilometers over 6 months. Nearby stars appear to shift ever so slightly against much more distant stars. The angle is incredibly tiny. For many stars, it is less than 1 arcsecond, about the apparent size of a coin viewed from several kilometers away. Yet modern instruments can detect these minute changes with astonishing precision. Unfortunately, Andromeda is far too distant for simple parallax to measure directly with useful accuracy. The angle becomes so unimaginably small that even our finest measurements struggle. So astronomers climb to the next rung of what they call the cosmic distance ladder. Each rung supports the next. Nearby stars help calibrate special variable stars. Variable stars help measure nearby galaxies. Nearby galaxies help calibrate even more distant objects. It is less like using one ruler and more like building a staircase toward the edge of the observable universe. Every step depends upon the strength of the previous one. That is why astronomy values independent confirmation so highly. If several different methods produce the same answer, confidence grows stronger. It is a little like asking several experienced bakers how much flour belongs in a loaf of bread. If everyone independently arrives at nearly the same amount, you begin trusting the recipe, except in this case, the recipe measures galaxies. And thankfully, no one burns the kitchen. Once astronomers know Andromeda's distance reasonably well, another surprisingly simple idea appears. Angles. Stand outside and hold your hand at arm's length. Your little finger covers about 1 degree of the sky. Your fist spans roughly 10 degrees. Everything in the sky occupies some apparent angle. The moon appears about half a degree wide. The sun appears almost exactly the same size in our sky, a delightful coincidence that allows total solar eclipses. Andromeda's visible core occupies only a modest angle, but long-exposure photographs reveal much more of its faint outer disk stretching several degrees across the heavens. Now comes the beautiful part. If you know two things, how far away something is, and how large it appears in the sky, you can calculate its true size. It is basic geometry, no magic required. Suppose you stand 100 meters away from a building. You know its apparent width. A few calculations later, you determine its actual width without touching the walls. Scale that same mathematics upward by millions of light years, and suddenly galaxies become measurable. The numbers become enormous. The geometry stays wonderfully ordinary. As observations improve through larger telescopes and more sensitive cameras, astronomers noticed Andromeda kept extending farther than expected. Every generation of instruments uncovered fainter stars surrounding the bright spiral. It was almost like discovering that an island visible above the ocean actually possessed vast underwater slopes hidden beneath the surface. The bright spiral was only the beginning. Today, estimates place Andromeda's visible stellar disk at roughly 220,000 light-years across, making it significantly larger than the Milky Way's bright disk, depending on exactly how astronomers define the edge. And galaxies rarely provide tidy borders. Some measurements differ slightly. That uncertainty is perfectly normal. Nature does not draw galaxies with permanent marker. Instead, stars become gradually fewer toward the outskirts. There is no sharp line saying, "Galaxy ends here." Historians still argue whether earlier 20th century estimates underestimated Andromeda because telescopes simply could not detect its faintest outer stars, or because astronomers interpreted the available data too conservatively, probably a little of both. Science often advances by seeing what was always there. One wonderfully quirky discovery is that amateur astronomers occasionally underestimate Andromeda's size simply because their telescopes show only its brightest regions. Through a modest telescope, it can actually appear smaller than in a good photograph. The galaxy hasn't changed. Your camera is simply more patient than your eyes. Patience, as it turns out, is one of astronomy's greatest superpowers. You drift closer in your imagination. The bright central bulge swells before you. Graceful spiral arms curl outward like enormous whirlpools frozen in slow motion. Dark lanes of cosmic dust trace elegant arcs through billions of stars. You now appreciate that every visible feature has been carefully measured. Not by anyone flying around the galaxy with a gigantic ruler, but through generations of careful observation, mathematics, and relentless curiosity, it feels strangely satisfying. Humans, standing on one tiny planet orbiting one ordinary star, manage to calculate the dimensions of a galaxy millions of light years away. Not perfectly, but remarkably well. There is something deeply hopeful about that. Our species may be small. We may argue over trivial things. We occasionally lose our television remote for 3 consecutive days only to discover it beneath a cushion. Yet somehow we also figured out how large Andromeda is. Civilization contains delightful contradictions. As your gaze lingers across the immense spiral, another thought quietly emerges. Knowing Andromeda's diameter is impressive, but size alone tells only part of the story. A galaxy can be larger without necessarily containing more mass. It can spread its stars differently. It can hide enormous quantities of invisible matter. And it can resemble our own Milky Way in ways that are both familiar and surprising. The next step is not merely asking how big Andromeda is. It is asking how it compares with the only galaxy you have ever truly called home. Your eyes move gently from Andromeda back toward the Milky Way, then return again, almost as though comparing 2 ancient portraits hanging side by side in a quiet gallery. From a distance, they seem like close relatives. Each displays graceful spiral arms, a bright central bulge, ribbons of dark dust, and billions upon billions of glittering stars. If you didn't know better, you might think they were nearly identical, like twins, cosmic twins, perhaps, although, like many siblings, one insists on being just a little bigger. For years, astronomers debated exactly which galaxy deserved the title of the larger spiral. Older estimates often suggested that the Milky Way and Andromeda were remarkably similar in size. As telescopes improved and fainter stars became visible, however, Andromeda gradually revealed a broader stellar disk than many scientists had expected. Today, the bright disk of Andromeda is generally estimated to span around 220,000 light-years, while the Milky Way's bright stellar disk measures roughly 100,000 to 120,000 light-years across, depending on where astronomers choose to define its edge. That last phrase is important. Galaxies refuse to have tidy borders. Imagine asking where a fog bank officially ends. You can point toward thinner and thinner mist, but finding an exact boundary becomes surprisingly difficult. Galaxies behave much the same way. Stars become increasingly sparse until eventually they blend into the surrounding darkness. Nature has little interest in drawing straight lines. One of the most important historical milestones came during the 20th century as radio astronomy transformed our understanding of galaxies. By observing clouds of neutral hydrogen gas rather than visible starlight alone, astronomers discovered that galaxies often extended much farther than photographs initially suggested. Invisible gas quietly whispered, "There's more out here," and scientists listened. You drift a little closer in your imagination. The Milky Way stretches beneath you like a luminous pinwheel. Andromeda shines ahead with similar elegance. Both galaxies possess magnificent spiral arms where new stars continue to form from cold clouds of gas and dust. These stellar nurseries glow softly as newborn stars illuminate their surroundings. Neither galaxy is frozen in time. Both are constantly changing. Stars are born. Stars age. Stars quietly fade away. The overall appearance remains graceful, even while countless individual stories unfold within. Now consider the stars themselves. For many years, Astronomers believed Andromeda contained roughly 1 trillion stars, making it comfortably richer than the Milky Way. More recent studies suggest that estimate may have been somewhat generous. Modern observations indicate Andromeda likely contains several hundred billion stars. Still an extraordinary population, and probably somewhat more than the Milky Way, although the exact number remains uncertain because counting stars inside galaxies is remarkably challenging. After all, nobody is sitting beside the galaxy with a giant clicker saying 300 billion, 300 billion and one. That would be an exhausting internship. Instead, astronomers estimate stellar populations using brightness, stellar evolution models, and observations of representative regions. It is more like estimating the number of trees in a vast forest by carefully studying sections of it, rather than counting every trunk individually. Science often favors elegant estimates over impossible tasks. Then comes mass. Here the story becomes surprisingly interesting. You might naturally assume that the larger galaxy must also be dramatically heavier. Not necessarily. For decades, Andromeda was thought to outweigh the Milky Way by a comfortable margin. Recent measurements, however, paint a subtler picture. The total masses of the two galaxies, including stars, gas, dust, and enormous quantities of dark matter, appear to be surprisingly similar. Some studies even suggest the Milky Way may rival Andromeda in total mass despite its somewhat smaller visible disk. That seems almost backwards. How can the larger-looking galaxy fail to dominate the scales? Because what you see is only part of the story. Much of every galaxy's mass is invisible. Dark matter, which you will explore in greater detail later, surrounds both galaxies in colossal halos, extending far beyond their bright stars. Those halos contain far more mass than all the visible stars combined. Imagine comparing two icebergs. One rises slightly higher above the water. The other hides a somewhat larger foundation beneath the surface. Judging by appearance alone becomes impossible. Galaxies behave in a remarkably similar way. One delightfully quirky fact is that astronomers sometimes jokingly refer to these competing mass estimates as a kind of galactic sibling rivalry. Every few years, improved measurements shift the balance ever so slightly, and headlines occasionally proclaim a new winner. The galaxies themselves remain magnificently indifferent. They have never entered the competition. Humans invented it. As you continue your peaceful voyage, notice another important similarity. Both galaxies rotate, not quickly by everyday standards. A single orbit around either galactic center takes hundreds of millions of years. If our solar system completes one full circuit around the Milky Way, approximately every 230 million years or so, then since the age of the dinosaurs, the Sun has traveled around the galactic center only a little more than once. That realization quietly reshapes your sense of time. Entire chapters of Earth's biological history occupy only a fraction of one galactic year. Historians still argue whether certain ancient cultures truly imagined the heavens as dynamic systems rather than perfectly unchanging spheres. While many early civilizations recognized celestial motion with remarkable accuracy, interpreting their cosmological ideas remains an active area of scholarly debate. Whatever their conclusions, they could never have imagined galaxies rotating over hundreds of millions of years. The timescales simply exceed ordinary human experience. You allow yourself to picture the Milky Way and Andromeda as two vast dancers slowly circling through the darkness. Neither rushes. neither hesitates. Gravity conducts the performance with infinite patience. The choreography unfolds over billions of years. No audience could watch it from beginning to end. Except, perhaps, the universe itself. Another comparison emerges. The central bulges of both galaxies contain older populations of reddish-yellow stars. Their spiral arms sparkle with younger, hotter blue stars. Great lanes of dust weave through each disk, supplying raw material for future stellar generations. They are built from the same cosmic ingredients: hydrogen, helium, gravity, time. Those simple components combine to create structures so magnificent that they almost seem impossible. Yet the universe has been assembling galaxies for over 13 billion years. Practice, apparently, makes perfect. You smile quietly. Even the finest architect on Earth would struggle to design a building containing hundreds of billions of suns. Building inspectors would probably have questions. Lots of questions. As your attention lingers on Andromeda's graceful spiral, you begin appreciating that comparing galaxies is rather like comparing oceans. One may stretch a little farther. Another may contain slightly more water. Both remain so vast that the differences hardly diminish either one's grandeur. The Milky Way is not made less beautiful because Andromeda appears somewhat larger. Andromeda is not made less fascinating because its total mass may closely resemble our own galaxies. Instead, together they reveal something profound. Nature often repeats successful patterns on unimaginable scales. Spiral galaxies are among the universe's most elegant creations, each unique in detail while sharing a familiar underlying design. And now that you've compared these two cosmic giants from afar, a more personal question begins to emerge. Suppose you actually tried to cross Andromeda itself. How long would such a journey take? The answer, unsurprisingly, is measured not in days, years, or even civilizations, but in spans of time so immense that they make the age of recorded human history feel like the briefest flicker of starlight. The comparison between the Milky Way and Andromeda slowly settles into the background as your imagination begins to ask a wonderfully impractical question. What if you actually tried to cross Andromeda? Not just admire it from afar, not simply measure it with elegant geometry, but travel from one edge of its luminous disk to the other. The idea sounds straightforward enough. Until you remember that this is a galaxy, galaxies have a remarkable talent for making ordinary journeys completely ridiculous. Imagine that you begin at one of Andromeda's outer spiral arms. Behind you, the faint glow of scattered stars gradually disappears into the immense darkness beyond the galaxy's visible edge. Ahead stretches an ocean of stars, gas, dust, and invisible matter extending for roughly 220,000 light-years. Already your destination sounds less like a road trip and more like a lifelong commitment. Actually, several million lifetimes. Let's begin with the fastest traveler you know. Light. A beam of light leaving one edge of Andromeda would require approximately 220,000 years to reach the opposite side of the visible disk. Remember that for a moment. Light, the undisputed speed champion of the universe, still needs over 200,000 years. If the fastest thing that can exist takes that long, perhaps packing extra sandwiches would be wise. Now replace light with something more familiar. Imagine one of humanity's fastest spacecraft. The Parker Solar Probe, launched by NASA, has reached speeds approaching 700,000 kilometers per hour during close passes around the Sun. That sounds breathtaking. On Earth, It certainly is. At that velocity, you could fly around the equator dozens of times before breakfast. Space has different standards. Even traveling at such astonishing speed, crossing Andromeda would require tens of millions of years, long enough for continents on Earth to drift noticeably, long enough for entirely new mountain ranges to rise while older ones slowly eroded away, long enough that future paleontologists might study the remains of cities that have not even been built yet. Your remarkable spacecraft, meanwhile, would still be quietly cruising between stars. You begin to appreciate why astronomers rarely discuss travel time with cheerful optimism. Suppose instead you boarded a commercial airliner. Let's be generous and assume it cruises at about 900 kilometers per hour. Crossing Andromeda would take on the order of tens of billions of years, longer than the current age of the universe itself. Your in-flight meal service would become memorable. Somewhere around year 8 billion, a flight attendant might ask, "Would you care for tea or coffee?" You would probably answer, whichever arrives first. The passengers behind you might still be waiting to recline their seats. Fortunately, this is only an imaginary journey. As you continue drifting peacefully through Andromeda, another surprising realization appears. Despite containing hundreds of billions of stars, the galaxy does not feel crowded, quite the opposite. The nearest neighboring stars remain separated by enormous distances. If you could shrink the Sun to the size of a marble, the nearest star would still lie hundreds of kilometers away at the same scale. Most of the galaxy is astonishingly empty. This is one of astronomy's favorite paradoxes. Galaxies appear densely packed in photographs because you view trillions of kilometers compressed into a flat image. Reality is dominated by space itself, vast, quiet, almost completely empty. As your journey carries you inward through one spiral arm, glowing nebulae drift past like delicate clouds illuminated from within. Young blue stars shine intensely, burning their nuclear fuel much faster than quieter yellow stars like our Sun. Massive stars live spectacularly, but briefly. Smaller stars live patiently. The universe seems equally comfortable with both lifestyles. You notice clusters of stars hanging together like luminous jewels scattered across velvet. These star clusters preserve some of the oldest stellar populations in the galaxy. Many formed billions of years ago, when the universe itself was still comparatively young. One remarkable historical fact is that astronomers gradually realized during the 20th century that star clusters act almost like cosmic clocks. By studying their stars, scientists estimate their ages with surprising accuracy, allowing them to reconstruct much of a galaxy's history. Each cluster becomes another chapter in an unimaginably long autobiography. Some pages remain perfectly readable. Others have faded with time. A particularly quirky observation fascinates researchers. Certain stellar streams stretching across Andromeda appear to be the shredded remains of smaller galaxies that wandered too close and were gradually torn apart by gravity. Imagine breadcrumbs scattered across a forest path, except each breadcrumb contains millions of stars. Gravity, though gentle over short times, proves extraordinarily persuasive over billions of years. Historians still argue whether every visible stellar stream in Andromeda can be confidently linked to known ancient merger events, or whether some originated through more complex interactions that remain poorly understood. The debate continues because galaxies possess wonderfully messy histories. No two grow in exactly the same way. You continue your crossing. Thousands of light years pass beneath you as effortlessly as drifting clouds. Dark dust lanes twist elegantly through the spiral arms, hiding newborn stars inside cold molecular clouds. Somewhere within those invisible cocoons, future planetary systems quietly begin taking shape. Perhaps rocky worlds are forming. Perhaps oceans will someday exist. Perhaps somewhere, billions of years from now, curious beings will look toward the Milky Way and wonder whether another civilization ever gazed back. The thought feels strangely comforting. Astronomy often reminds you that curiosity itself may be one of the universe's most widespread qualities. As the galactic center gradually approaches, the density of stars increases. The sky here would look utterly unlike Earth's night. Instead of isolated bright stars sprinkled across darkness, countless suns would fill every direction. Night, if it could still be called night, would glow softly all around you, yet collisions between stars would remain extraordinarily rare. Even in this crowded region, the distances separating individual stars remain immense. Space continues to be mostly space. Nature clearly brought emptiness in bulk. Eventually you realize that crossing Andromeda is less about reaching the opposite side than appreciating the extraordinary patience built into the cosmos. Nothing hurries. Stars complete orbits over hundreds of millions of years. Galaxies evolve across billions. Even your imaginary voyage becomes another reminder that the universe measures time with breathtaking calm. You no longer feel the need to rush. There is nowhere urgent to arrive. Only another graceful stretch of spiral arm waiting ahead, filled with ancient stars, quiet nebulae, and countless stories unfolding at a pace perfectly suited to the age of galaxies. And as you drift deeper into this immense stellar city, another question quietly presents itself. What exactly fills all of this astonishing space? Because crossing Andromeda is one thing, understanding what lives inside it is an entirely different adventure. Your long voyage across Andromeda gradually slows, not because the galaxy has become any smaller, but because your attention begins settling on the countless inhabitants of this immense cosmic city. Up to this point, you've admired the galaxy as a whole, a magnificent spiral stretching across more than 200,000 light years. Now you begin looking at what actually lives inside that enormous space. The first surprise is that there is no single kind of star. If someone casually says, Andromeda contains hundreds of billions of stars, it sounds as though every star were identical, lined up neatly like identical light bulbs. The universe has never been that organized. Instead, Andromeda resembles an enormous city filled with neighborhoods of every age and personality. Some regions sparkle with energetic young blue stars, blazing brilliantly but living comparatively short lives. Other regions glow softly with older yellow and orange stars that have quietly orbited the galaxy for billions of years. Each population tells a different chapter of Andromeda's story. You drift through one of the graceful spiral arms. Here, enormous clouds of hydrogen gas stretch for dozens or even hundreds of light years. They appear dark in visible light because thick dust blocks the glow behind them. Yet inside these cold clouds, gravity slowly performs its patient work. Tiny clumps become denser. Those clumps become warmer. Eventually, pressure rises until hydrogen nuclei begin fusing together. A new star is born, no dramatic countdown, no cosmic ribbon-cutting ceremony, just gravity quietly succeeding once again. It is astonishing to think that every atom in your own body was forged inside stars that formed billions of years before the sun existed. The carbon in your cells, the oxygen you breathe, the calcium in your bones, all were created through nuclear fusion deep inside ancient stars before being scattered across space. You are, quite literally, made from recycled stardust. The universe has an excellent recycling program. Its paperwork, however, takes a few billion years. One of the great historical achievements of 20th century astronomy came when scientists finally understood how stars generate their energy. Before that breakthrough, many ideas were proposed, including gravitational contraction and even chemical burning. It was only through advances in nuclear physics that astronomers realized stars shine because hydrogen nuclei fuse into helium deep within their cores. That discovery explained not only why stars glow, but how the chemical elements themselves are created. The story of galaxies suddenly became the story of everything. You continue drifting deeper into the spiral arm where brilliant blue stars dominate the view. These giants burn astonishingly hot. Some shine tens of thousands of times brighter than the sun. Yet their brilliance comes at a price. They consume their nuclear fuel with breathtaking speed compared with smaller stars. If stars had personalities, these would be the enthusiastic friends who sprint through every activity while somehow still insisting they aren't tired. The quieter red dwarf stars, meanwhile, sip their fuel so slowly that many will outlive the current age of the universe. Slow and steady occasionally wins on a cosmic scale. Surrounding many young stars are glowing nebulae, vast clouds illuminated by intense ultraviolet radiation. The gas shines with delicate reds, blues, and pinks, creating some of the most beautiful structures visible through powerful telescopes. Photographs often make these regions appear almost unreal. Yet they are entirely natural. Gravity, light, and chemistry collaborate to create works of art requiring no artist. You soon notice another kind of stellar gathering, globular clusters. These ancient spherical collections contain hundreds of thousands of stars packed much more closely together than those in the galaxy's disk. They orbit far above and below the spiral arms, like loyal companions circling a great kingdom. Many of these clusters formed more than 12 billion years ago. Some were already ancient long before Earth itself existed. Imagine visiting a library where every book predates your planet. That is roughly what studying globular clusters feels like. Astronomers treasure them because they preserve clues about the earliest stages of galactic history. One wonderfully quirky discovery is that Andromeda possesses significantly more known globular clusters than the Milky Way. Hundreds have been identified, and researchers continue discovering additional candidates using increasingly sensitive observations. It is almost as though Andromeda has spent billions of years enthusiastically collecting stellar antiques. The galaxy clearly appreciates vintage items, no dusting required. As you leave the globular clusters behind, the bright central bulge gradually grows before you. Here, older stars dominate. The brilliant blue giants become less common, replaced by countless yellow, orange, and reddish stars. Quietly orbiting the galactic center, the atmosphere feels calmer somehow, more reflective. The stellar population here remembers much earlier chapters of the galaxy's history. Every orbit has been repeated countless times over billions of years. You imagine standing on a hypothetical planet near the bulge the night sky would scarcely resemble the one above Earth. Instead of seeing a few thousand visible stars, the heavens would blaze with countless brilliant suns packed across every direction. Darkness itself would become difficult to find. Yet, despite this crowded appearance, individual stars would still remain separated by enormous distances. Even here, collisions remain extraordinarily unlikely. Space never entirely gives up its emptiness. Historians still argue whether Andromeda's unusually large central bulge formed primarily through ancient galaxy mergers or evolved gradually through slower internal processes over billions of years. The evidence supports elements of both ideas. Nature, as usual, refuses to choose the simplest answer. Galaxies often write their histories using several pens at once. As you continue inward, another fascinating realization emerges. Stars are only part of the population. Between them drift enormous quantities of gas and microscopic dust grains composed of carbon, silicon, oxygen, and heavier elements forged inside previous generations of stars. Without that dust, planets like Earth would never form. The tiny particles floating almost unnoticed between the stars eventually become worlds. There is something beautifully poetic about that. Dust is not the end of a story. It is the beginning of another. Somewhere inside Andromeda, at this very moment, rocky planets are almost certainly forming around newborn stars. Some may resemble Earth. Others may be unlike anything your imagination can easily construct. Whether any harbor life remains one of astronomy's greatest unanswered questions. The universe keeps that secret remarkably well. You smile quietly. Perhaps it enjoys a little mystery. After all, if galaxies revealed everything immediately, there would be far fewer reasons to keep looking upward. Your journey through Andromeda now feels less like crossing an object and more like wandering through an immense living ecosystem. Stars are born. Stars evolve. Stars quietly enrich the galaxy with heavier elements before giving rise to future generations. Everything connects. Nothing stands entirely alone. Even you carry atoms whose ancestors likely participated in similar cycles billions of years ago. And yet, astonishingly, everything you've admired so far, the glowing spiral arms, the brilliant clusters, the ancient bulge, the shimmering nebulae, represents only the visible portion of Andromeda. Beyond the bright stars lies something vastly larger, something almost completely invisible. A hidden halo stretches far beyond the graceful spiral, quietly dominating the galaxy in ways your eyes could never reveal. And that unseen giant is where your journey continues next. The last bright spiral arm slowly fades behind you. Not because Andromeda has ended. Far from it. Instead, you've reached one of astronomy's most surprising discoveries. The galaxy extends far beyond the graceful spiral that appears in photographs. The beautiful disk filled with glowing stars is only the part that easily catches your eye. Beyond it lies something much larger. Something quieter, something almost completely invisible. If galaxies were trees, the bright spiral would be the trunk and branches. The hidden halo would be the enormous root system stretching silently through the surrounding ground, supporting everything while rarely attracting attention. The universe has always appreciated understated architecture. You continue drifting outward from Andromeda's luminous disk. The familiar spiral arms gradually become thinner and more widely spaced. Bright clusters grow rarer. Nebulae disappear into the darkness. At first glance, it feels as though you've left the galaxy entirely. You haven't. Scattered far beyond the visible disk are ancient stars moving through enormous looping orbits. They are so sparsely distributed that from nearby you might travel for hundreds of light years without encountering another star. This vast region is known as the stellar halo. Unlike the elegant flattened spiral disk, the halo surrounds the galaxy in every direction, forming a roughly spherical cloud extending astonishingly far into space. The stars here are among the oldest members of Andromeda, many formed early in cosmic history, long before the galaxy acquired its present appearance. Some probably originated elsewhere entirely. Over billions of years, smaller galaxies wandered too close to Andromeda. Gravity gradually stretched and tore them apart, scattering their stars into long streams that eventually blended into the surrounding halo. Rather than destroying history, gravity preserved it. The halo became a museum. Every stellar stream is another ancient exhibit. One of the major historical breakthroughs in modern astronomy came when increasingly sensitive telescopes began detecting these faint stellar streams around nearby galaxies. During the late 20th and early 21st centuries, astronomers realized galaxies are not isolated islands growing peacefully on their own. They are shaped by countless encounters, some gentle, some dramatic, most unfolding so slowly that no human lifetime could ever witness them from beginning to end. Historians still argue whether Andromeda experienced one especially massive merger several billion years ago, or accumulated its enormous halo through many smaller collisions spread across cosmic history. The evidence continues to evolve as astronomers map ever fainter stellar structures. Like detectives reconstructing an ancient crime scene, they examine tiny clues left behind in the motions and chemical compositions of stars. The galaxy remembers. You simply need patience to read its memory. As you drift farther outward, something even stranger begins to emerge. The stars themselves no longer dominate the galaxy. Instead, an invisible component quietly takes over: dark matter. You cannot see it. You cannot touch it. It neither emits nor reflects light. Yet without it, Andromeda, and indeed almost every galaxy in the universe, would behave very differently. Imagine watching leaves swirl around an invisible whirlpool beneath the surface of a pond. You cannot see the whirlpool directly, but the leaves reveal its presence. Astronomers study galaxies in much the same way. When they measured how rapidly stars orbit Andromeda's center, they discovered something puzzling. The outer stars moved far faster than expected. According to the visible matter alone, those stars should have drifted away into intergalactic space long ago. Instead, they remained securely bound. Something unseen was holding everything together. That mysterious gravitational glue became one of the strongest pieces of evidence for dark matter. One delightfully quirky comparison often used by astronomers is that studying dark matter resembles attending a party where you never meet the host. Everyone talks about them. Everything suggests they're present. The entire event depends on them. Yet they remain frustratingly invisible. The universe can be wonderfully mysterious. You now imagine the dark matter halo surrounding Andromeda. It dwarfs the bright spiral. While the visible disk measures roughly 220,000 light-years across, the dark matter halo may extend more than 1,000,000 light-years from the galaxy's center. Pause for a moment. 1,000,000 light-years. That means the magnificent spiral you've admired throughout this journey occupies only a relatively small portion of the galaxy's full gravitational influence. It's like admiring the brightly lit stage while forgetting the enormous theatre surrounding it. The invisible part is far larger than the visible performance. Scientists estimate that dark matter accounts for the overwhelming majority of Andromeda's total mass. The stars, gas, and dust, beautiful though they are, represent only a small fraction of what is actually there. That realization quietly changes your perspective. Everything you've admired so far has been the cosmic equivalent of decorative icing. The cake itself remains unseen. Fortunately, invisible does not mean unknowable. Astronomers infer the shape and size of Andromeda's dark halo by studying the motions of stars, globular clusters, dwarf galaxies, and enormous clouds of gas. Every orbit becomes another clue. Every measurement strengthens the overall picture. Science often succeeds by studying effects rather than causes directly. You cannot see the wind either. Yet swaying trees reveal it immediately. Dark matter leaves similar fingerprints throughout the universe. As you continue outward, the darkness grows increasingly profound. Individual stars become astonishingly rare. The halo feels almost empty. Almost, yet gravity remains quietly present everywhere. You begin sensing Andromeda less as a collection of stars and more as an enormous gravitational landscape extending far beyond anything visible. The galaxy resembles an invisible mountain whose snowy peak alone rises above the clouds. Most of its structure remains hidden beneath. One particularly fascinating discovery is that the outer halos of the Milky Way and Andromeda may already be brushing against one another. Although the bright stellar disks remain separated by millions of light years, their vast dark matter halos could already overlap slightly as the galaxies slowly approach. If true, their interaction began long before the dramatic merger, still billions of years in the future. The dance has already started. The partners simply haven't reached the center of the ballroom yet. That thought feels strangely elegant. The universe rarely begins with fireworks. Instead, it whispers. Tiny gravitational influences accumulate over unimaginable spans of time until eventually entire galaxies respond. Patience once again proves to be gravity's greatest strength. You glance back toward Andromeda. From here, the familiar spiral appears almost modest, surrounded by an immense invisible kingdom, extending in every direction. The glowing stars now seem like lanterns suspended inside something vastly larger, beautiful, graceful, but only part of the whole story. You smile quietly at how often astronomy rewards humility. Just when you think you've reached the edge of understanding, another invisible layer appears, another hidden structure. Another reminder that reality is almost always richer than first impressions suggest. And deep within that brilliant central bulge, hidden beneath billions of surrounding stars, waits another remarkable resident. Unlike the quiet halo stretching across intergalactic space, this inhabitant occupies a region smaller than the solar system. Yet its gravity rivals millions of suns combined. Your journey is about to take you to the calm heart of Andromeda itself. Your journey gently changes direction. Instead of drifting outward into Andromeda's vast, invisible halo, you now glide back toward the glowing heart of the galaxy. The spiral arms slowly curve behind you. Ancient star clusters become more numerous. The density of stars gradually increases until the galaxy seems to wrap around you in every direction. Ahead, the bright central bulge shines with a warm golden glow. It looks peaceful, almost welcoming. If galaxies had living rooms, this would certainly be one of them. Of course, like many elegant living rooms, there's one feature everyone quietly notices. In the very center sits a supermassive black hole. Fortunately, it isn't trying to swallow the entire galaxy like an over-enthusiastic vacuum cleaner. Hollywood has been rather unfair to black holes. Reality is both stranger and much calmer. At the exact heart of Andromeda lies a supermassive black hole known as M31. Astronomers estimate it contains well over 100 million times the mass of our Sun. That number is difficult to picture. Imagine compressing the mass of more than 100 million suns into a region that, compared with the galaxy itself, is astonishingly tiny. The surrounding stars continue orbiting peacefully, held together by gravity in an elegant celestial dance. You slowly approach the central region. The night here would be unlike anything imaginable from Earth. Instead of a few thousand visible stars, millions would illuminate the sky. Every direction would sparkle with brilliant points of light, layered one behind another until darkness itself became difficult to find. Yet, despite this crowded appearance, individual stars still remain extraordinarily far apart. Even near the galactic center, space refuses to become truly crowded. The universe seems determined to preserve its favorite ingredient: emptiness. One of the greatest historical achievements in modern astronomy came when scientists learned how to measure the masses of invisible black holes. They cannot observe the black hole itself directly because no light escapes from within its event horizon. Instead, astronomers carefully study the motions of nearby stars. The faster those stars orbit, the stronger the central gravitational pull must be. It is remarkably similar to watching leaves circle an invisible whirlpool. You never see the whirlpool directly. You infer its existence from everything moving around it. The mathematics is elegant. The observations are painstaking. Together, they reveal one of nature's most extraordinary objects, the first direct image of a black hole, produced by the Event Horizon Telescope collaboration, famously showed the shadow of the supermassive black hole in Messier 87. Although Andromeda's own black hole has not been imaged in the same iconic way, the achievement demonstrated that humanity could actually observe the environment around one of these cosmic giants. That was once thought almost impossible. The impossible has a habit of becoming merely difficult. As you continue inward, something surprising becomes apparent. Andromeda's central black hole is quiet, very quiet. You might expect an object containing over 100 million solar masses to blaze with spectacular energy every moment of every day. Instead, it spends most of its time resting. Astronomers call such black holes relatively inactive because very little gas currently falls into them. Without fresh material spiraling inward, there is little fuel to power brilliant radiation. It is a little like owning an enormous fireplace with almost no logs. The fireplace itself remains impressive. It simply isn't roaring tonight. That peaceful nature is good news for any hypothetical observers nearby. Active supermassive black holes can produce enormous jets and intense radiation, dramatically affecting their surroundings. M31, by comparison, seems content to remain comparatively quiet. Perhaps even black holes appreciate an occasional nap, although one suspects their naps last several million years. You smile at the thought. No alarm clock could possibly compete. As you watch the stars orbit the galactic center, another fascinating realization emerges. The black hole, enormous though it is, contains only a tiny fraction of the galaxy's total mass. That sounds almost unbelievable. Surely something weighing over 100 million suns must dominate everything. Not when the galaxy itself contains hundreds of billions of stars, plus an even larger reservoir of dark matter. The central black hole is immensely powerful nearby. On the scale of the entire galaxy, however, it resembles the heart of a giant creature, essential, influential, yet occupying only a small portion of the whole body. One delightfully quirky discovery about Andromeda's nucleus puzzled astronomers for years. The galaxy appears to possess a curious double nucleus, as though two bright central concentrations of stars existed instead of one. At first, this seemed almost impossible. Had Andromeda somehow grown two centers? Further study suggested a more subtle explanation: the stars near the black hole orbit in elongated paths, creating an illusion of two separate brightness peaks rather than one perfectly symmetrical cluster. Nature once again proved more creative than anyone expected. Historians still argue whether every detail of Andromeda's unusual central structure can be explained entirely through stellar orbital dynamics, or whether ancient merger events also contributed significantly to its present appearance. The discussion remains active because galactic centers preserve clues from billions of years of evolution. Each new observation adds another piece to an extraordinarily old puzzle. You continue hovering peacefully above the nucleus. Stars sweep around the invisible center in graceful arcs, each following gravity's patient instructions. None rush. None hesitate. Every orbit reflects a balance between motion and attraction refined across immense spans of time. There is something deeply calming about such predictability. Gravity never forgets its equations. The stars never miss their appointments. Meanwhile, somewhere on Earth, someone is still trying to remember where they left their house keys. Perspective is healthy. Looking outward from the galactic center, you notice the magnificent spiral stretching away in every direction. Dust lanes curl elegantly through the disk. Blue star-forming regions sparkle along distant arms. Globular clusters drift through the surrounding halo. The entire galaxy seems connected, every component participating in one enormous gravitational symphony. The black hole does not command the performance alone. It simply anchors the quiet center, while billions of stars contribute their own movements. Together they create the graceful spiral you first admired from afar. And yet, Andromeda's influence extends even beyond its own stars. Dozens of much smaller galaxies orbit this giant, bound by its immense gravity, like tiny companions circling a majestic parent. Some are ancient, some bear scars from close encounters. All help reveal just how far Andromeda's gravitational reach truly extends. Your next destination lies among those faithful little neighbors, patiently circling the giant they have called home for billions of years. The bright nucleus of Andromeda gradually recedes behind you. The quiet supermassive black hole remains hidden beneath billions of surrounding stars, patiently holding court at the galaxy's center. As you drift farther outward once again, the immense spiral slowly comes back into view, its graceful arms curling through space like delicate brush strokes painted across a black canvas. But this time, your attention is drawn beyond the spiral itself. Something smaller moves through the darkness, then another and another. They are galaxies too. Tiny compared with Andromeda, yet galaxies all the same. you begin to appreciate that giant galaxies rarely live alone. Just as planets gather around stars, smaller galaxies often gather around larger ones, held together by gravity across astonishing distances. These companions are called dwarf satellite galaxies. The word dwarf sounds almost dismissive. In astronomy, however, it simply means smaller than the great spiral giants. Many dwarf galaxies still contain millions, or even billions, of stars, hardly tiny by everyday standards. Only the universe could casually describe a galaxy containing hundreds of millions of suns as small. Perspective remains one of astronomy's favorite jokes. One of Andromeda's best-known companions is Messier 32, often shortened to M32. Nearby travels another faithful companion, Messier 110, also called M110. These two satellites were actually discovered centuries ago and appear in the famous catalogue compiled by Charles Messier during the 18th century. Messier never intended to create a catalogue of beautiful deep sky objects, quite the opposite. He was hunting comets. Faint, fuzzy objects repeatedly fooled him into thinking he had discovered another comet, only to reveal themselves as permanent celestial residents. Rather than becoming frustrated forever, he began cataloguing these impostors. Future generations thanked him enormously. Imagine accidentally creating one of astronomy's most famous catalogues simply because the universe kept playing practical jokes. Even galaxies occasionally enjoy a sense of humor. As you approach M32, it appears very different from Andromeda itself. Instead of magnificent spiral arms, it forms a compact, smooth glow. Long ago, this little galaxy probably looked quite different. Many astronomers suspect repeated close encounters with Andromeda stripped away much of its original structure, leaving behind the dense remnant visible today. Gravity can be remarkably gentle over short periods. Over billions of years, however, it becomes an expert sculptor. Nothing escapes its patient influence forever. Nearby M110 follows its own graceful orbit. This satellite contains older stars, but also preserves pockets of gas and dust where modest star formation continues. Each dwarf galaxy possesses its own unique personality. Despite living under Andromeda's overwhelming gravitational influence, it is a little like villages surrounding an enormous city. Each develops its own history, its own character, its own quiet rhythm of life. One important historical milestone came as increasingly powerful telescopes revealed more and more satellite galaxies around both the Milky Way and Andromeda. Throughout the 20th and 21st centuries, astronomers realized these giant spirals possessed far richer families than previously imagined. New companions continue to be discovered even today because many are extraordinarily faint. Finding them is rather like searching for tiny fireflies beside an enormous lighthouse. The lighthouse attracts most of your attention. The fireflies require patience. Historians still argue whether Andromeda originally possessed significantly more satellite galaxies than it does today, with many having already merged into the larger galaxy, or whether its current family has remained relatively stable over much of cosmic history. The evidence continues to accumulate. Galactic genealogy is surprisingly complicated. Families, it seems, have always been complicated. You continue drifting through the outskirts of Andromeda, watching dozens of smaller galaxies orbit at enormous distances. Some follow elongated paths, others trace gentler, more circular routes. Each orbit reflects billions of years of gravitational negotiation. No traffic lights required. just physics. One delightfully quirky observation has fascinated astronomers in recent years. Several of Andromeda's satellite galaxies appear to occupy a surprisingly thin plane, almost as though many companions are orbiting within a shared, flattened arrangement rather than moving randomly in all directions. This pattern remains something of a mystery. Some researchers suggest ancient mergers helped organize the satellites. Others believe the apparent alignment may partly reflect observational limitations. Nature has not yet revealed the full answer. You pause for a moment to appreciate scale once again. The satellites orbit hundreds of thousands of light years from Andromeda's center. Some venture even farther. Their journeys require billions of years to complete. Imagine celebrating your birthday once every orbital revolution. You would receive remarkably few birthday cards. On the bright side, nobody could accuse you of aging quickly. As you watch these quiet companions, another realization emerges. Astronomers do not study dwarf galaxies simply because they are charming little neighbors. They study them because the satellites reveal the true extent of Andromeda's gravity. Just as the Moon reveals Earth's gravitational influence through its orbit, Andromeda's satellites trace the invisible shape of the galaxy's enormous dark matter halo. Every companion becomes another measuring instrument. Without realizing it, each tiny galaxy helps astronomers weigh its gigantic host. The satellites act almost like leaves floating across an invisible pond. Their motions reveal currents beneath the surface that your eyes could never detect directly. Science often advances by observing what moves rather than what remains hidden. As your journey continues, you notice faint streams of stars stretching behind several dwarf galaxies. These delicate ribbons mark places where gravity slowly pulls stars away from their original homes. Nothing dramatic happens overnight. Instead, every orbit gently reshapes the satellites bit by bit. Century after century, million year after million year, gravity possesses extraordinary patience. It never becomes tired. It never loses focus. Given enough time, it quietly transforms entire galaxies. You cannot help smiling. The universe seems wonderfully confident. There is never any rush. The stars will arrive exactly where gravity intends. Eventually, looking back toward Andromeda, you now see far more than a single spiral galaxy. You see the center with its quiet black hole. You see the glowing bulge of ancient stars. You see sweeping spiral arms rich with stellar nurseries. You see the immense invisible halo stretching outward. And beyond all of that, you see a family of smaller companions faithfully orbiting their giant neighbor. The galaxy has become an entire ecosystem. Every component influences every other. Nothing exists in complete isolation. Yet even this magnificent family portrait captures only one moment in an ever-changing story. Gravity has another chapter already prepared. The Milky Way continues drawing closer. Andromeda continues approaching. Their invisible halos already begin to mingle. Over billions of years, the distance between these two spiral giants will steadily shrink until one extraordinary future unfolds, not a violent collision in the ordinary sense, but a slow, majestic meeting unlike anything humanity has ever witnessed. That patient encounter is now waiting just beyond the next quiet stretch of cosmic night. The family of dwarf galaxies gradually fades into the darkness behind you, each continuing its patient orbit around Andromeda, as though nothing extraordinary lies ahead. Yet something extraordinary most certainly does. far across intergalactic space, the Milky Way continues its own graceful journey. Every second that passes, the distance between these two spiral giants shrinks by just a tiny amount. No telescope watching over a human lifetime could notice the change directly. Even thousands of generations would see almost no difference. Gravity, however, keeps perfect time. It never misses an appointment. The meeting has already been scheduled. The invitation was sent billions of years ago. You simply happen to live very early in the countdown. At first, the idea sounds alarming. Two galaxies colliding? Surely that must be one of the most violent events imaginable. Hollywood certainly thinks so. Entire planets exploding. Stars smashing together. Everything bursting into spectacular fireballs while dramatic music plays in the background. Reality politely declines the screenplay. The truth is far more elegant and, surprisingly, much calmer. The Milky Way and Andromeda are separated by about 2.5 million light-years today, but Andromeda is moving toward us at roughly 110 kilometers every second. That sounds incredibly fast. And by everyday standards, it certainly is, fast enough to cross an entire continent in well under a minute. Yet compared with the enormous distance between galaxies, even that impressive speed means the encounter remains billions of years away. Astronomers estimate the first close passage will occur in roughly 4 to 5 billion years. You have plenty of time to finish your cup of tea, possibly even 2 cups. One of the landmark discoveries that revealed Andromeda's approach came through spectroscopy. By examining the slight shift in the galaxy's light toward the blue end of the spectrum, astronomers realized it was moving toward the Milky Way rather than away from it. That was an astonishing result. Most distant galaxies appear to recede because the universe itself is expanding. Andromeda breaks the trend locally because gravity between our two giant galaxies is stronger than the expansion of space over this comparatively short cosmic distance. It is rather like two friends walking toward each other on an airport moving walkway that's slowly carrying everyone backward. The walkway still moves. The friends simply walk faster. As the galaxies draw nearer, something subtle happens long before their visible disks ever touch. Their enormous dark matter halos continue overlapping more extensively. Invisible gravity begins reshaping both galaxies from afar. Neither galaxy notices all at once. Instead, tiny gravitational nudges accumulate over millions of years. The dance begins with whispers. Eventually, Andromeda grows larger in the Milky Way's sky. Not over centuries, not over civilizations, over hundreds of millions of years. Future observers, if anyone is around to witness it, would watch a faint smudge slowly expand until graceful spiral arms stretched across a significant portion of the heavens. Night after night, century after century, the changes would remain almost imperceptible, yet compared over immense spans of time, the sky itself would transform. One delightfully quirky thought often shared by astronomers is that no individual creature could ever perceive the entire approach naturally. The process unfolds far too slowly. It would be like trying to watch a mountain grow. You need geological patience. Fortunately, imagination provides exactly that. As the galaxies finally experience their first close encounter, the greatest surprise emerges. Stars almost never collide. This sounds completely backwards. After all, two galaxies containing hundreds of billions of stars are passing through one another. Surely countless stellar crashes must occur. Remarkably, no. Remember those immense distances separating individual stars. Even in dense galactic regions, stars are tiny compared with the enormous volumes between them. If the Sun were the size of a grain of sand, the nearest comparable grain might still be dozens of kilometers away. Galaxies appear crowded. Reality remains overwhelmingly empty. The odds of two individual stars striking each other directly are extraordinarily small. Instead, gravity does almost all the work. Stars change their orbits, gas clouds compress. New waves of star formation ignite. The galaxies become distorted, stretched into magnificent tidal tails and graceful arcs. It is less like two swarms of bees colliding, more like two enormous clouds drifting through one another, while invisible currents reshape every path. Historians still argue whether early computer simulations underestimated the complexity of galactic mergers because available computing power was so limited. Modern simulations reveal astonishingly intricate structures, showing bridges of stars, looping streams, and vast shells emerging during the interaction. Each generation of computers uncovers new layers of beauty. The universe rewards better mathematics. One fascinating possibility concerns our own solar system. The Sun is expected to survive the merger because it still has billions of years of life remaining. Its orbit around the galactic center, however, may change dramatically. Rather than remaining in roughly its present location, the solar system could be flung into a completely different region of the newly forming galaxy. Imagine living in the same house while someone quietly relocates the entire neighborhood. No moving boxes required, the scenery simply changes. Fortunately, the planets themselves should remain safely bound to the Sun, Earth, if it still exists in recognizable form, would continue orbiting our familiar star. The larger danger to Earth's distant future comes not from Andromeda, but from the Sun itself gradually becoming brighter as it ages. Long before the galactic merger finishes, our star will already be approaching the later stages of its life. The galaxies, meanwhile, continue their patient choreography without concern. You watch in your imagination as the graceful spirals begin losing their familiar shapes. Arms stretch outward, dust lanes twist. Great rivers of stars stream into intergalactic space before eventually falling back under gravity's influence. The once distinct galaxies slowly become one, not destroyed, transformed. That distinction matters. Nature often prefers transformation to annihilation. The meeting lasts billions of years. There is no single moment labeled collision. Instead, countless smaller gravitational interactions gradually reshape everything. The dance concludes only after repeated passes, each removing a little more of the original spiral structure. Eventually, a new giant galaxy emerges. Astronomers have even suggested playful nicknames for this future creation. One of the most popular is Milkomeda. Scientists, it turns out, occasionally enjoy terrible puns. You cannot really blame them. After spending decades calculating orbital dynamics, perhaps one earns the occasional cosmic dad joke. As the vision slowly fades, you realize something quietly reassuring. The future merger sounds dramatic because the timescales are so immense. Yet, from the perspective of any single lifetime, the galaxies remain almost perfectly serene. Tonight, Andromeda still hangs peacefully beyond the Milky Way. Its spiral arms continue turning, its stars continue shining, its patient journey continues. And if you could somehow watch the entire encounter from outside both galaxies, you would witness one of the grandest dances the universe has ever choreographed. slow, graceful, and astonishingly beautiful. Soon, you'll imagine standing beneath the changing skies of that unimaginably distant future, watching Andromeda grow brighter overhead one silent night at a time. The great galactic dance now feels less like an abstract prediction and more like a slow-motion story already unfolding. You know that Andromeda is approaching. You know that gravity has quietly been arranging this meeting for billions of years. Now, instead of observing the event from somewhere far outside both galaxies, imagine something far more personal. Imagine standing beneath Earth's night sky in that unimaginably distant future. Of course, there is one important detail. Earth itself almost certainly will not be the same world. In fact, our planet may no longer be habitable by the time Andromeda begins dominating the sky. The sun will gradually grow brighter over the next several billion years, making Earth's surface increasingly hostile long before the galaxies complete their merger. So think of this as a peaceful thought experiment. A quiet window into a future sky. You step outside beneath a perfectly dark evening. At first, everything feels familiar. The Milky Way still arches overhead, its pale river of stars stretching across the heavens, exactly as countless generations have admired before you. Andromeda remains a soft, fuzzy patch, barely noticeable unless you know where to look. Centuries pass, nothing changes. Millennia pass, still almost nothing. Even hundreds of thousands of years make remarkably little difference. The universe teaches patience more effectively than any meditation instructor ever could. Eventually, after millions upon millions of years, Andromeda begins to grow. Not suddenly, never suddenly. Its faint glow slowly expands until careful observers notice that it appears slightly larger than ancient star charts recorded. Future astronomers compare observations separated by geological spans of time. The measurements agree. The galaxy is getting closer. One of the fascinating historical achievements that made such predictions possible began with careful measurements of Andromeda's motion during the 20th century. By combining spectroscopy, precise distance estimates, and increasingly sophisticated computer simulations, astronomers learned not only that Andromeda was approaching, but approximately how the future encounter would unfold. It is remarkable. Humanity predicted the choreography of galaxies billions of years before the performance reached its climax. That is confidence built on mathematics. As another 100 million years quietly passes in your imagined timeline, Andromeda's spiral structure gradually becomes easier to distinguish. No telescope required. The bright central bulge grows broader. The graceful arms begin revealing themselves as faint luminous arcs crossing the night. People living beneath such skies, wherever intelligent observers might exist, would no longer speak of Andromeda as merely another galaxy. It would become part of everyday life. Children would grow up seeing two giant spiral galaxies overhead. They might find old photographs of today's night sky strangely empty. Perspective changes remarkably quickly when you have several 100 million years available. One delightfully quirky possibility, often mentioned by astronomers, is that future calendars might include no special event marking Andromeda's arrival. Why? Because every generation would inherit almost exactly the same sky as the one before. The changes remain too gradual for anyone to notice directly. It would be like watching your own hair grow. You know it happens. You simply never catch it in the act. Historians still argue whether future civilizations assuming any exist, would preserve continuous astronomical records long enough to appreciate the galaxy's gradual expansion across the heavens, or whether knowledge would be interrupted by cultural changes impossible to predict. The debate reminds you that astronomy depends not only upon the universe, but upon observers willing to keep watching. The stars remain patient. Civilizations are another matter. As Andromeda continues approaching, the night sky becomes increasingly spectacular. Its luminous disk eventually stretches many times wider than the full moon. Dust lanes become visible under truly dark conditions. Bright star-forming regions sparkle within the spiral arms. The galaxy transforms from a faint smudge into a breathtaking celestial landscape. You imagine lying comfortably beneath that future sky. No city lights, no passing airplanes. Only two enormous spiral galaxies suspended across the darkness. The sight would almost certainly inspire poetry, and probably a great many neck cramps. Looking upward for hours has always carried occupational hazards. Eventually, the first close passage arrives. From your imagined viewpoint, the heavens begin changing more noticeably. The familiar spiral patterns become distorted. Great arcs of stars stretch across the sky. Long luminous streams connect the galaxies like delicate bridges woven from countless suns. The transformation remains extraordinarily slow by human standards, yet compared with earlier ages, the pace now feels almost energetic. Gravity has finally begun revealing the choreography it prepared over billions of years. Gas clouds collide far more frequently than stars do. These encounters compress enormous regions of hydrogen, triggering bursts of new star formation. Brilliant blue stars illuminate fresh stellar nurseries throughout both galaxies. The heavens become richer with light. Ironically, a galactic collision can become an engine for creating stars rather than simply destroying structures. Nature rarely wastes raw materials. It reorganizes them. Some regions blaze with newborn stellar clusters. Others gradually fade as older stars continue their quiet evolution. Everywhere you look, change unfolds with graceful inevitability. You begin appreciating that galaxies resemble living ecosystems more than rigid machines. Nothing stands still. Everything evolves. One particularly charming comparison imagines the merging galaxies as two vast flocks of birds slowly interweaving across the sky. Individual birds rarely collide. Instead, the entire flock changes shape through countless tiny adjustments. The beauty lies not in sudden impacts, but in coordinated motion. Galaxies behave remarkably similarly. The longer you observe, the more harmonious the process appears. Far from feeling frightening, the merger becomes almost hypnotic. You breathe quietly. Stars continue their patient orbits. Nebulae glow softly. Dark dust traces elegant curves through luminous clouds. Even enormous gravitational interactions unfold with astonishing calm. The universe possesses remarkable confidence. It never seems anxious about tomorrow. Eventually, after repeated close passages spanning billions of years, the familiar spiral shapes gradually disappear. In their place emerges a new giant galaxy. Its exact appearance remains uncertain, but many simulations suggest a large elliptical or lenticular system containing the combined stellar populations of both original galaxies. Some astronomers affectionately call this future creation Milkomeda. The nickname may sound slightly silly. The galaxy itself certainly will not. By then, trillions of stars will share a common gravitational home. You imagine looking up one final time, The sky no longer resembles today's heavens, yet something essential remains unchanged. The stars still shine, gravity still guides them, the universe still unfolds with extraordinary patience. Only the scenery has evolved. As that peaceful vision slowly fades, another thought quietly takes its place. Everything you've learned about Andromeda, its size, distance, motion, hidden halo, companions, and future, depends upon an extraordinary achievement. Human beings discovered all of this while standing on one tiny planet, orbiting one ordinary star. How? That elegant story begins with the remarkable tools and ingenious methods astronomers use to measure a galaxy they can never visit. The imagined future sky slowly dissolves, and with it fades the vision of two great spiral galaxies weaving together across billions of years. Your attention gently returns to the present. You are once again standing, at least in your imagination, on a small planet, orbiting an ordinary yellow star, looking up at a faint glow in the constellation of Andromeda. It is almost unbelievable that everything you've learned tonight, its immense diameter, its hidden halo, its ancient stars, its quiet black hole, its family of satellite galaxies, and even its distant future, has been discovered without anyone ever traveling there. No spacecraft has visited Andromeda. None has even come remotely close. The distance remains far beyond the reach of today's technology. So how do astronomers know so much? The answer is wonderfully simple. They become exceptionally good at listening to light. Every photon arriving from Andromeda carries information, not words, not pictures, just tiny clues, brightness, color, direct, timing, like individual notes in a symphony. Each clue may seem insignificant on its own. Together, they reveal an astonishingly detailed portrait of an entire galaxy. You imagine holding a single raindrop in your hand. From that one drop, you might learn almost nothing, but collect billions of raindrops over many years, and you begin understanding the climate itself. Astronomers treat light much the same way. The universe sends countless photons every second. Scientists patiently collect them. One of the greatest historical revolutions in astronomy began with the invention of spectroscopy during the 19th century. By passing starlight through prisms and diffraction gratings, astronomers discovered that light separates into a rainbow filled with tiny dark and bright lines. Those lines are fingerprints. Every chemical element leaves its own distinctive pattern. Hydrogen, helium, oxygen, iron, calcium. Each announces its presence through light. Suddenly, astronomers could determine what distant stars were made of without ever touching them. It must have felt almost magical. Imagine identifying the ingredients of a cake simply by examining the color of its candlelight. The universe, it turns out, is surprisingly cooperative. It labels its atoms. As you continue your quiet journey, enormous observatories begin appearing around you. High atop isolated mountains, giant telescopes patiently wait beneath clear skies. Their mirrors gather faint light that has traveled for millions of years, concentrating it onto exquisitely sensitive instruments. One of the most influential observatories for studying nearby galaxies has been the Mauna Kea observatories, where several powerful telescopes have helped astronomers investigate the structure and motion of Andromeda above Earth's atmosphere. The Hubble Space Telescope transformed your understanding even further. Freed from atmospheric turbulence, Hubble resolved individual stars inside Andromeda with breathtaking clarity. Instead of seeing a soft blur, Astronomers could distinguish countless separate suns. It was like walking closer to an enormous mosaic until individual tiles finally became visible. Each newly resolved star became another piece of evidence, another clue, another tiny voice joining the cosmic conversation. One delightfully quirky fact about Hubble is that even after decades of operation, it continued producing discoveries nobody anticipated when it first launched. Astronomy has an amusing habit of rewarding curiosity with completely unexpected surprises. Telescopes rarely say exactly what you expected. They usually reply, "Well, that's interesting." Meanwhile, radio telescopes quietly contribute their own perspective. Unlike visible light telescopes, they detect long radio waves emitted by cold hydrogen gas spread throughout galaxies. This invisible gas maps spiral arms extending beyond what ordinary photographs easily reveal. It is almost like hearing whispers in a dark room, after everyone else assumed the room was empty. Different wavelengths reveal different stories. Infrared telescopes peer through dense dust clouds that block visible light. Ultraviolet telescopes highlight energetic young stars. X-ray observatories detect some of the hottest and most violent environments. No single telescope sees the whole galaxy. Together, they create a richer portrait than any instrument could achieve alone. Science, much like an orchestra, performs best when many voices work together. Historians still argue whether certain early observations of spiral galaxies deserved greater recognition because later technological advances confirmed ideas that initially seemed speculative. This happens surprisingly often in science. An observation may appear uncertain for decades before improved instruments quietly vindicate it. Patience once again proves invaluable. You imagine astronomers spending countless nights collecting data, not glamorous nights filled with dramatic discoveries every hour. Most science is quieter than that. Careful calibration, repeated measurements checking results, correcting tiny errors, beginning again. The greatest breakthroughs often emerge from extraordinary consistency rather than extraordinary excitement. It is a comforting thought. Deployments matters. Another ingenious technique involves measuring the motions of stars themselves. Using the Doppler effect, astronomers determine whether stars move toward or away from Earth by examining tiny shifts in their spectral lines. A star moving toward you compresses its light slightly toward the blue. Moving away, it shifts gently toward the red. The effect resembles the changing pitch of a passing ambulance siren. Except instead of sound waves, the universe sings in light. By combining the motions of countless stars, scientists reconstruct how Andromeda rotates. They infer the distribution of visible matter. They uncover evidence for dark matter. They even estimate the galaxy's total mass, all without leaving Earth. There is something profoundly inspiring about that achievement. Human beings remain physically tiny. Our planet is ordinary. Our telescopes occupy only a minuscule corner of one spiral galaxy. Yet curiosity allows us to understand objects millions of light-years away. Knowledge travels farther than rockets. You smile quietly. Perhaps that is humanity's true superpower, not speed, not strength, curiosity. As the observations accumulate across generations, Andromeda gradually transforms from a distant blur into a richly understood neighbor. Its spiral arms become familiar. Its star clusters receive names. Its satellite galaxies reveal their histories. Its future collision with the Milky Way becomes increasingly predictable. Every new observation adds another brushstroke to an already magnificent painting, yet no matter how detailed the portrait becomes, mysteries remain. Some questions grow more intriguing every year. Some answers create entirely new puzzles. The better you understand Andromeda, the more you realize how much remains hidden beneath the surface. And that may be the most beautiful lesson of all. Because the next part of your journey leads not towards certainty, but toward the quiet mysteries that continue keeping an astronomers awake, while the rest of the world sleeps. The more clearly Andromeda comes into focus, the more mysterious it becomes. That might sound backwards. Surely understanding something should make it less mysterious. Sometimes it does, but astronomy has a charming habit of replacing every answered question with 3 new ones waiting patiently just beyond the edge of discovery. You have learned how large Andromeda is. You have crossed its spiral arms. You have wandered through its ancient halo. You have visited its quiet central black hole and met its family of satellite galaxies. Yet countless mysteries still linger, hidden among its billions of stars. You drift peacefully above the galaxy once more. From this vantage point, the graceful spiral looks complete, balanced, almost timeless. Reality, however, tells a far more complicated story. Astronomers now believe Andromeda did not grow peacefully in isolation. Instead, like many large galaxies, it appears to have been assembled piece by piece through countless mergers with smaller neighbors over billions of years. Imagine building a magnificent castle, not by carving one enormous block of stone, but by gradually collecting thousands upon thousands of individual bricks from many different places. Galaxies grow in remarkably similar ways. Every merger leaves subtle fingerprints behind. A stream of stars here, a distorted orbit there, an unusual chemical composition somewhere else. The clues remain scattered throughout the galaxy like pages from an ancient diary. Reading them simply requires extraordinary patience. One particularly intriguing mystery concerns Andromeda's surprisingly large central bulge. Compared with the Milky Way, its bulge contains a greater concentration of older stars. Why? Did one especially dramatic merger billions of years ago reshape the galaxy? Or did several smaller encounters gradually produce the same result? Astronomers continue debating the answer. Historians still argue whether the earliest observational hints of Andromeda's unusual structure received enough attention before modern simulations highlighted their importance. As often happens, old observations sometimes become newly valuable when viewed through fresh ideas. The universe rarely wastes information. You continue drifting through faint stellar streams extending across the galaxy's halo. These rivers of stars seem almost delicate. Yet each represents the remains of an ancient galaxy gradually torn apart by gravity. Some streams have been mapped in exquisite detail, others remain only partially understood. Researchers continue discovering additional structures as telescopes become increasingly sensitive. It is rather like exploring an ancient city buried beneath layers of sand. Every careful excavation uncovers another forgotten street, another hidden doorway, another unanswered question. One delightfully quirky fact is that astronomers occasionally nickname especially faint stellar streams after everyday objects because their true nature is difficult to recognize at first. A long arc may receive an informal nickname before detailed analysis reveals its remarkable origin. Even galaxies appreciate temporary nicknames. The universe seems remarkably tolerant of human creativity. Another mystery concerns Andromeda's dark matter halo. You already know that the invisible halo extends vastly beyond the bright spiral. But what exactly is dark matter? That remains one of the greatest unanswered questions in all of physics. Scientists know it exists because of its gravitational influence. Galaxies rotate too rapidly without it. Galaxy clusters contain far more gravity than visible matter alone can explain. The large-scale structure of the universe itself bears its unmistakable signature. Yet, the particles responsible have never been directly identified. Imagine hearing footsteps echoing through an empty house. You know someone, or something is moving, you simply cannot see who it is. Dark matter remains that unseen visitor. Patiently leaving footprints across the cosmos, you pause to admire the galaxy once again. Its spiral arms shimmer softly. Dust lanes trace graceful curves. Ancient globular clusters continue orbiting through the halo. Everything appears peaceful, yet beneath that calm exterior lies an intricate history. Scientists continue unraveling one observation at a time. Another fascinating puzzle involves Andromeda's past rate of star formation. Evidence suggests the galaxy experienced periods of unusually vigorous stellar birth followed by quieter eras. What triggered those bursts? Nearby mergers? Internal instabilities? Changing supplies of cold gas? The answer remains uncertain. Galaxies possess memories. Learning to interpret them takes time. You smile gently. The universe seems rather fond of keeping laboratory notebooks written in starlight. One of the greatest strengths of modern astronomy lies in computer simulations. Supercomputers model billions of particles interacting through gravity across cosmic time. Researchers compare these virtual galaxies with real observations, adjusting assumptions until simulations begin resembling nature. The processor resembles assembling an impossibly complicated puzzle without knowing exactly what the finished picture should look like. Each improvement brings theory and observation a little closer together. Neither stands alone. One informs the other. Historians still argue whether future generations will look back on today's simulations as charmingly simple. Just as modern astronomers smile at early computer models from decades past, the pattern seems inevitable. Every generation believes its tools are impressive. The next generation quietly improves them. Knowledge grows one careful step at a time. As you continue floating above Andromeda, another realization settles comfortably into your thoughts. Mystery is not a flaw in science. It is its fuel. If every question already possessed a complete answer, curiosity would have nowhere left to travel. Instead, each discovery opens another doorway. Each measurement suggests another experiment. Each observation inspires another night beneath the stars. There is something wonderfully hopeful about that. Humanity has not reached the end of understanding. Far from it. You imagine astronomers centuries from now studying Andromeda with instruments beyond today's imagination. Perhaps enormous space telescopes spread across millions of kilometers, perhaps observatories on distant worlds, perhaps techniques not yet conceived. They, too, will inherit unanswered questions. They, too, will discover surprises. The galaxy will continue rewarding careful attention. Because Andromeda is not merely an object. It is an ongoing conversation between the universe and every curious mind willing to listen. You take one final slow look across its immense spiral. The countless stars no longer feel anonymous. The dust lanes seem familiar. the halo stretches quietly into darkness. The satellite galaxies continue their graceful orbits. Even the hidden black hole at the center now feels like an old acquaintance, the question that began tonight. How big is the Andromeda Galaxy? Has gradually transformed into something richer. Size was only the beginning. Understanding brought perspective. Perspective brought wonder. And now, with every piece of the story gathered together, only one gentle task remains: to step back, to see the entire picture at once, and to let the astonishing scale of Andromeda quietly settle into your imagination before the stars themselves begin carrying you peacefully towards sleep.